GERAD Researcher Seminar. Today, we have the pleasure to receive Brigitte Jaumard. Brigitte holds a Concordia University Researcher Tier 1 on the optimization of communication networks in the Computer Science and Software Engineering Department at Concordia University. Her research focuses on mathematical modeling and algorithm design for large-scale optimization problems arising in communication networks, transportation and logistic networks, and in automated mechanism design. She also recently started to work on machine learning models and algorithms in the same area of applications. She also holds the position of Chief Scientist at CRIM Computer Research Institute of Montreal, and is a Senior Advisor of Gaia, Global Artificial Intelligence Accelerator Ericsson in Montreal. Besides, she currently leads the research group of the SUF project at Siena, a networking systems, services, and software company. And her presentation will talk about the development of the current EDF platform within this SUF project. So without further ado, I will let Brigitte go ahead with the presentation. Brigitte, you have the floor, and this presentation will be recorded. Thanks.
Okay, thank you, Olivier. Indeed, that's correct. I'm going to talk about the SOF project at Siena. I'm going to explain what it is. And I'm currently on a sabbatical. And so it has been a particular sabbatical, no traveling, but a lot of collaborations with networking companies, and in particular with Siena, with Exfo, and with Ericsson. So the presentation of today, it's mainly in relation with the project at Siena. So I'm going to give you some brief overview. And I want to talk today within this seminar about a core, I would say, combinatorial optimization problem in the context of 5G networks. I will not mention in that presentation any machine learning algorithms. I'm only going to focus for today on the graph or mathematical programming algorithms that are currently developed. And but for sure, there are also several ongoing projects with machine learning approaches. And eventually, I'll be happy to talk about them in the future. So this project, as mentioned, it's related, so it's in collaboration with Siena. It's within the SOF project, where SOF stands for Cell Optimizing Fabric. So it is sponsored by Encore. So what is Encore, just to give you an idea? So the federal government, it's an initiative of the federal government in order to ease and make the development of 5G faster. So there are different companies which are involved in Encore. So for sure, you have networking operators, so Ericsson and Siena. But you have also Thales, IBM, and CGI for the key involved companies. So what does it mean? It means that Encore has received a budget in order to sponsor research in the area of 5G, and not only for academics, but also for SMEs, with the idea that they could use the 5G Encore testbed in order to get familiar with 5G and potentially to have experience or preliminary project with 5G. So within Encore, so there is this SOF project where the core idea is the arrangement of different components, systems that needs to dynamically discover, organize, optimize themselves among different common business goals. So we'll go more in the detail of what this means in the coming slides. So the soft project at Siena, it's a whole team of people, and the research part is mainly done by universities, that is graduate students, throughout MyTax project, where the industrial counterpart is Encore. So the leading universities are the ETS, University of Ottawa, and the University of Western Ontario. So there are about today 40 students, including PDF, postdoctoral fellow, and with projects related to the research aspect of this soft infrastructure. Okay. So today I will talk only about one part of the soft project, the one that is related to what is called 5G service request provisioning. And the key contributors, so there is Dr. Kim Koa Nguyen, who is a faculty member at ETS. There are several PDF. So for sure, there is Rui Duong, who is with CRIM, Tin Tran, who is with ETS, and several master and PhD students. So I'm going to talk about some particular project, but of course, each student that is here has a very specific research question to investigate. So before I move to the details, let me give you a very high-level 5G overview, and I'll do it only through illustrations. So if you look at this one, okay, in the lower part, we assume that we have two operators, operator A and operator B. So each of them operates a network that is described in the very bottom part, where on the left you have the radio part. Then you have the access network, and then you have the core networks. And today, whenever you are talking about networks, there is the traditional network component with network equipment, but you have also a lot of compute resources. And that's the reason why on this illustration of networks, you see different clouds. And whenever we say clouds, as you all know, we mean data centers. Okay. So today, networks are moving more and more to networks with key software components, and where networks are more and more operated with software, and ideally in an automated way. So that's where there is a huge evolutions in the management of the networks, where in the past it was mainly hardware equipment, while today it's mainly software. Okay, so let's go a little bit more in the detail of the specific problem of 5G network provisioning. So when we are talking about this problem, we have a first input, which is the network and its compute resources. So the network can be described by a graph, where each node is associated with a router. So that's the blue symbols that you see. And some nodes, some routers have compute capabilities. So whenever they have compute capabilities on this drawing, you see that they are directly connected to a data center. So as you see, not every node has compute capabilities. And then whenever we describe a communication network, so you have nodes which are connected, and between every pair of nodes, then you have parameters. So in short, you have the delay. So that's what you can see on the numbers with the numbers of those links. And you have a bandwidth capacity. Again, that's the second number that you see on each of the link. Now, for those of you who are not familiar with networks, here you see what is in graph theory is called an undirected network, but it's just for the representation. Okay, the edges here are just to indicate which nodes are connected. And in practice, whenever you have a connection between two nodes, you have two links, two directed links, one in each direction. So in other words, whenever we are talking about networks, we are talking about directed graphs, and they are a little bit particular in the sense that you can represent them as I just described with connections between pair of nodes. And whenever there is a connection, there are two directed links, one in each direction. So for the problem I want to talk about today, the first input, it's a network and its computer resources, with the network described, of course, by its set of nodes, its set of links, and then you have delays and bandwidth numbers on each link. Second input, you have, and I'm going to explain what it is, you have a set of NFV and a set of SFC. So let's start with NFV. So NFV, it's an acronym that stands for Network Function Virtualization. So as I mentioned, looking at the evolution of networks today, the idea is that you want to virtualize as much as you can all network functions. So here I've put some examples. So packet inspections, firewall, load balancing. So in the past, those functions used to be in hardware devices. And today, the evolutions, especially with 5G, is they will be all implemented as a software. And for their operations, for sure, we need heavy compute resources. So on these slides, you see some examples of traditional or classical NFV. So the most common example that you find in the papers is the firewall, but you can see here other functions. Now, service chain, SFC, sorry, it stands for Service Function Chain. So a service function chain, it's a set of network functions. And traditionally, or very often, a service functions chain is described as an ordered sequence of functions, okay? So here you have an illustration. So again, you can see the network here. So it's simplified. So we have three nodes, three routers, and then you have two requests, okay, two service requests. The number one, the red one, and number two, the blue one. So whenever you want to define a service request, it comes in its characteristics with the SFC that is attached to it. And by SFC, as I just explained, it's a sequence of an ordered sequence of functions. So for example, for the request number 1, it comes with a service chain that includes IDS for the first function, and then the firewall for the second function. So whenever you want to provision this function, you need to make sure that it goes through a node, a router that has compute resources, such that the first one will host IDS function. And then it doesn't need to be the next node, but later on the path, you have one that is, you have a node hosting a firewall function. So if I take the blue here on this example, the service chain is limited to one function, and it's a load balancer. Okay. So most service chains are defined, as I just mentioned, as an ordered sequence of functions. So here on these slides, on the top, you recognize the function chain that was illustrated in one of the previous slides as a sequence of 3 functions. The first one being a firewall, second one IDS, and the third one load balancer. But not all service chains are defined as an ordered sequence of functions. You could have, as here in the bottom, a partial order where you may allow 2 functions to be taken care in parallel, or let's say there are different ways to interpret the representation here. That is, you could have the choice, either you go to a firewall or you go to a monitor, but you don't need to satisfy both, you don't need to go through both functions. Now, in general, if I would like to give a definition or a general definition of a service chain, I would say that it corresponds, or it is associated to a set of functions, and the precedence relations of those functions are described with what we usually call a DAG, that is a directed acyclic graph. And that's what you see here in the example on the bottom of the slide. Okay, so we're close to to be able to have the problem statement of service request provisioning. So so the first input, it was a network, and the set of compute nodes, that is which node were associated with compute resources. So on these representations, the node again are these router symbols with the red cross. And then you see that some of them, not all of them, are with compute resources. Indeed, those associated with compute resources do have a gray cube. Now, as I mentioned, whenever you define a service request, you need to specify the source node, the destination node, and a service function chain. Okay, so here we have 2 requests. The number 1, that is with the service function chain, that is A followed by C. Okay. Now the VNF, they are not hosted by all the routers. Okay, they are available only in some routers. Okay, and the placement of those VNF has to be optimized so that you have them in different locations, but in such a way that whenever you have a service request, you are able to satisfy the delay requirements. So let's say here in this first example that you can see that we have 6 nodes with compute capabilities, but for 3 of them, maybe it's low traffic, or let's say we have not yet fully deployed, so that no function is available on the nodes number 3 and so on. So no function is available on those routers. However, on the top routers, you have a given number of VNF which are available. Okay? So whenever you want to find a path from source to destinations and you have a service functions, you need to find a path that will first encounter A, then B, then C. For example, if we are talking about service request number 2. What does it mean? It means that eventually we'll end up with a path containing loops. So if I take the example of the first request, we first need to go to A, okay? So that's what we, I believe I've inverted the two SFC. So for the first request, we first need to go to A, okay? That's the red function. No, sorry, I'll start again. So let's go through the request number 2. So we first need to go through a node that contains A. So that's what we do at this node, okay? As the router is with compute resources, hosting in particular the function number 1. Then we go to the second router where B and C are available, okay? But the destination is this particular node. So in order to reach the destination, then we have no choice. The path goes through a loop in order to be able to reach the destination. So what we see here is that in order to find a route satisfying these service chains defines as an ordered sequence of functions, we may end up with routes or paths containing loops. And that's a first reason why the traditional shortest path algorithms may have trouble, as they usually assume that you don't want to have loops. Now, what I want to illustrate on this new slide is that for sure the placement of the VNF plays a critical role, okay? So here in the two examples, we have exactly the same numbers of VNF replica, okay? But they are not in the same locations, okay? So I'm not going to talk too much about it in the first part of the presentation, but for sure in practice, you have to wisely determine the placement of those VNF, because it will have an impact on the length of the path and the fact that you'll be able to serve the path with their delay requirement. So now we are almost ready for the problem of the problem statement. So as I mentioned, as an input, we have a network. We have the compute, the locations of the compute resources. We have a list of a VNF, at least of service chain. And the traffic that we need to route is defined by a set of service requests where each service request as a source, as a destination, as a service function chain, and that's what I'm adding on these slides. It has bandwidth and delay requirement. So delay requirement, the most common one, it's between the source and the destination. So you need to be able to reach your destination within a given delay. There may be additional delay between two successive functions. So you don't know at the beginning where you are going to use those functions, but you need to select the locations in such a way that, for example, between function B and function C, you don't exceed a given delay. And last requirement, it's the bandwidth. So the request comes with a bandwidth consumption. So every link has a bandwidth capacity. And then you need to be able to find a path so that you can satisfy the bandwidth requirement of the request. So that's for the problem statement. So I hope this is clear for everybody. So now how to solve that problem? So if we want to solve the problem in practice, so the traffic, as you know, it's dynamic. So it means that at given times, you have a new service request, and you have eventually ending request. So whenever there is an ending request, that's good. You free the resources of that request. So whether it's the bandwidth or the compute resources. So I'm going to talk a little bit in the first part of the presentation about solving the problem, assuming that you have dynamic traffic and that you have to provision the request as they come in. Before going to the algorithm, I want to discuss the layered graph, which is sorry for the phone, which is a trick in order to go around the loop issue. And it works as follows. So let's say that you have a request. So for sure, it has a source and a destination, and it has a service chain. So let's assume that it's a service chain with 3 functions. So what you can do is build this layered graph where you have several copies of the network, and you have as many copies as the number of function plus 1. So in the first copy that you see in the bottom, you are going to search for a path from the source to a node that hosts the first function in your service chain. In other words, you are going to look for a path from the source to a node hosting function number 2. So here, in this example, I've assumed that there are only 2 nodes with compute resources and only 2 nodes where you can have access to the function number 2. So those 2 nodes are the red nodes. Okay, so let's assume that here I operate function 2 at this particular first red node. Then we will take care about the second function in the service chain. And for that, we'll move to the second copy of the graph. How do we do that? So we are going to add what you see, some of them, those dotted links, which I'm going to call cross-layer links. and they are defined as follows. So between the copy, the first copy and the second copy, you have a cross-layer link for each occurrence of function 2. So here I didn't represent all of them. I would have 2. So the one that I represented, and then a second one that would go from the second occurrence of F2 to the same node, but in the second copy of the graph. In other words, the only way I can move from the first copy to the second copy is after going through a node hosting the first function of the service chain. So now I move to the second copy, and I need to take care about the second function in the service chain. So let's say that this function is available in 2 nodes. Okay, the nodes which are corresponding to the blue nodes here. So if we go through this node in order to get access to function 5, then we can move again to the next graph where we will take care about the next function, and locations where it is available, it corresponds to the yellow nodes. Okay? So it means that from the arrival node in this copy, we need to reach a yellow node before exiting. And then the last copy, it's in order to reach the destination. So here we don't have much to do in the last copy because the node where we start in that copy is the destination node as well. So what is the interest of this layer graph? Its main interest is to make it possible to look for paths without any loop. Okay, so that is, whenever you are in a given layer, you have no reason to go through a loop. Okay, you start from a given node, and you need to look for a path such that you reach the next function of the service chain. Okay. Now, if you would collapse those all the graphs on a single copy of the graph, that's where you may discover that you have loops. But if you search the path on the layered graph, then you can use the traditional paths algorithms because you are looking for paths without any loop. So if we want to solve the real-time problem, we need to use distributed algorithms. And in this particular problem, we need to use distributed shortest path. Okay, because you may have given a first incoming request, so you look for a path with that has the proper resources for that path, but you may have a second incoming request before you had the time to do the reservation of the path for the first incoming request. So in other words, you have a concurrent request competing for resources in the network. And for that reason, you need to use distributed algorithms in addition to the fact that in practice, you don't have a view of the overall graph, but at a given node, you are only aware of its neighbors. So what is the state of the art today for distributed shortest path? Well, not surprisingly, as in a graph theory, computing shortest path is one of the central problems in distributed computing. And for sure, it has been studied for a long time. Now, there has been recent progress with the work of Elkin in 2017, who proposed a new improved exact algorithm for distributed shortest path. For sure, I won't go through it. It's not necessarily a very complex algorithm, but if you want to go through the complexity of it, that's where it's quite complex. So because of this recent improvement, some people are even talking about breakthrough. There is a renowned interest in the computations of distributed shortest path. Now, if I come back to the problem that we need to solve in practice, so what we need is a distributed resource-constrained shortest path. So we need to have it distributed because at any given time, we don't have the global view of the network. Only for a given node, we have only the view of its neighbors. And in addition, we need to provision the compute resources, and we need to satisfy the service chain that is going through a given number of functions in a particular order. So for that reason, today, companies are still looking for efficient algorithm for this problem, because it requires the combinations of several algorithms. So it is a combination of distributed shortest path that have been studied mainly, I would say, in computer science. They need to have resource constraints shortest path. So for sure at GERAD, that's a problem that is well known, that has been well studied, but with various constraints. Indeed, I mentioned some of the constraints, not all of them. So for example, you could have additional constraints such as two particular VNF cannot be hosted on the same data center. Okay, you may have constraints, as I said, with a delay requirement between two successive VNF. And what is particular also is that for for a given VNF, since it's a software, you have different compute requirements. So the traditional ones are the CPU, the RAM, and the storage. And all those resources have to be available at the same node. Okay, so that is something that is a little bit uncommon in the context of constrained shortest path, at least in the context of what has been, for example, traditionally studied in optimization or operation research. And in addition, you need to take into account the delay and the bandwidth requirement. So the delay, if we are talking about end-to-end delay, that's not something that is unusual. For sure, it has been considered, and there are algorithms for that. And it's not a constraint that is difficult to take into account. Now, the bandwidth requirement, if you look at the literature for distributed shortest path, people are looking at the resources mainly for the nodes, but here you have also requirements for the links, because the bandwidth requirements, this is related to the links. So, conclusion of this in the context of the soft project at Siena, there are different algorithms that we are developing, where we are really trying to combine several existing algorithms, but still at the end, we need to make sure that those algorithms are real-time scalable. And I have a last comment about that. When in open research we develop heuristics, usually it's with the goal of having short computing times, okay? And in opposition to the computing times that are required by the exact algorithms. But very often when we develop heuristics, whether it's meta-heuristics or greedy heuristics, we look at the times, and then if you look at the publications, people are comparing their computational times. But those times that we get traditionally are not considered as good enough in order to answer the real-time requirements of the networks. So I would say that one of the biggest challenge, if we want to develop the exact graph algorithm, is to be able to meet the real-time requirements. And for that reasons, we may need to use heuristics. And definitively, there is no time for meta-heuristics. It's mainly greedy heuristics. But at the same time, you want to have, if possible, the optimal solution. So in other words, the best possible greedy heuristics. So even if we are looking at, in particular at that slides, we may say that, okay, not a big deal. I think just combine the best distributed algorithms with the best resource constraints algorithms, and then you get an algorithm for doing the network provisioning. Because of the real-time requirement, this is not something fully obvious. And if you look at the literatures in the context of networking, you will see that a lot of people today are working on this problem. Okay, so I don't have numerical results yet to present on this problem, at least on the real-time algorithms and on distributed versions. So hopefully we'll get soon some results in the team project that we have at Siena, but not yet. And to come back on what I said in the introduction, not only we are working on graphs algorithms, but we are also working on machine learning algorithms. So in the remaining part of the talk, I want to briefly discuss some exact algorithms that are not real-time, but that would be used in order to assess the quality of the heuristics or the quality of the machine learning algorithms. So the first paper I want to talk about, it's a paper that has been published in 2018, but which is still today, maybe not for long, the paper with the most efficient exact algorithm. Okay, and not surprisingly, because we are at GERAD, it relies on a column generation model. So what we have done in that piece of work is developed a column generation model where the variables of the master problem are those y, p, s, d, c variable. So such a variable is equal to 1 if a request is forwarded through a given path and 0 otherwise. So here, a request is defined by the source, the destination, the service chain, and the bandwidth requirement. In a subsequent paper, we added the delay as well. Okay, so for the objective, when we developed that model, I must say that this work was done prior to my collaboration with Sienna. And so the objective that we used was what was the commonly studied objective, that is the minimization of the bandwidth requirement. And in practice, it makes sense in the sense that it corresponds to the cost model, in the sense that you want to charge the customer for the resources that he's using in the network. However, here you may say that we forgot one part, that is to include the cost of the compute resources, and I would agree with that. So the model, I will not go through the detail of it, but as with many column generation model, you can really write it in a quite compact way. So the key constraints are that for every demand, we want to select only one path. We need to satisfy the link capacity. And we need to satisfy the node capacity. So here we had a little bit a simplification for the node capacity, which are indeed associated with the available compute resources at a given node. Okay, so this is the flow chart of the algorithm. So I believe that for several of you, this is well known. And I just want to say a few words about the results. So we use different networks. So the largest one was 50 nodes, and it corresponds to the Germany network. And we consider 4 different service chains. So the first one can be viewed as associated with a request that is typical of a web service. The last one, typical of a request that is associated with online gaming. So here I've put typical bandwidth rates and distribution of the traffic among those chains. Okay, so those who are a little bit familiar with networking, it is well known today that the biggest contribution of the traffic, and probably that it has even increased with the pandemic, it's here we use close to 70% of traffic associated with video streaming. So first table, it's the performance of the column generation algorithm in terms of the accuracy. So that is, we didn't develop a branch and price algorithm. That is, whenever we reach the optimal LP solution, we just solve the associated restricted master problem with Cplex. So we derive an ILP solution, and we can then compute an accuracy of the solution. As you can see, we could solve quite large, at least for the context of 5G networks, quite large instances, as for the Germany network, we had close to 10,000 requests. So having this algorithm, we use it for some analysis, and in particular, the impact of the number of compute nodes on the bandwidth requirement in the network. Okay? So so you may have the questions of why we don't have compute nodes everywhere, why we don't have compute resources for every router. Well, because it has a cost. And same thing for the functions, okay, such as the firewall. Ideally, you would like to have them available in every node, but you have to view a firewall today as a software, and with every software you have a license, and with every license you have a cost. So as a network operator, you want to buy the minimum number of license so that you can still satisfy your delay requirement. But of course, it has potentially an impact on the bandwidth requirement on your network. And that's what we studied here. So on the horizontal axis, for the first network, the internet network, which is the US network, we looked at increasing the number of nodes with compute capabilities. And then we look at the impact on the bandwidth. And of course, not surprisingly, as you increase the number of nodes with compute capabilities, you decrease the bandwidth requirements, because then you can have shorter paths, okay? So, and then here you can see it as well for Germany. So Germany network has 50 nodes. So we went up to the extreme, that is assuming that every node has compute capabilities. And for sure, you can significantly reduce the bandwidth requirement. So where is the best solution for a network operator? Well, you need to find the best compromise between the number of nodes with compute capabilities versus the bandwidth, the network bandwidth, the bandwidth that is available in the network. Okay? So, of course, we couldn't go with suggesting where is the compromise, because then you would need to have all the numbers with respect to the associated cost. Here, just for the fun, we plot the locations of the placement of the VNF. That is in one version of the algorithms. We can decide on the best placement of the functions, assuming that you have a bound on the number of occurrences. So here, so on the right, each color is associated to a given function, okay? So the firewall, that's the typical example. This is the black. And then in every node, you can see different heights, okay? They are associated to the percentage of requests that are served by that function in that location. And same results, but this time for the Germany network. So that so what we see, and that's not a big surprise, that is the locations are mainly concentrated in the middle of the network. And that's not a big advantage to put those compute capabilities on the nodes that are on the border of the network. And I'm almost done. So last part of the presentation, whenever we are talking about column generations, especially in the context of transports, usually there are not so many different decompositions. My experience working on in the area of networking is that for a given problem, you have quite often quite different decomposition that you can think of. And here it's just some ideas for quite different decompositions that we are currently exploring. Indeed, if you look at the papers in the context of IEEE papers, people are looking at what they call embeddings, but mainly for machine learning approaches. So what is the idea? I try to capture it again by those figures. So let's take an example where you have two requests, the red and the blue. And then you have a network represented here in black. So whenever you want to find a provisioning for a request, you can view it as the coordination of node and link mapping. What does it mean? Well, first, you are going to look or identify the nodes associated with the locations of the VNF, that is the function, okay? So there is a first phase where you do a node mapping. So you start with your network. You have a given service chain. Here, for the example, it's made of two functions. So what you do is you identify in the first step where you are going to the nodes where you are going to use the functions associated with the requirement of the service chain. And then you have a second phase where you do the link mapping, because for a given request, you need to go from the source to the first function of the service chain, then to the next function. So you need to connect those particular nodes. So here it's a very simple example. That is, when I connect, it's only one link, but in practice, on a bigger network, it can be a path. So for example, back to this slide, okay, I've identified those three nodes. And when you need to connect them, you can first connect them with what we call a virtual link, but it has to be mapped on a particular path on the physical network. Okay, and then this gives ideas of new column generation formulation, which is indeed a nested column generation. And I just wanted to take the opportunity of this problem to talk about nested column generation. So in the past 2 years, I've worked with several students on nested column generation. And for various optimization problems arising in the context of networks. So for sure, it's a lot of work when you want to do the implementation of it, but it appears that a quite efficient tool for solving problems. So here, I won't go through the detail because I think I'm almost at the end of my time, but we have used the ideas or reused the ideas of those papers talking about embeddings. And we managed to reuse those ideas in order to formulate a different decompositions and that corresponds to a nested decomposition, where in the low level pricing, all we need to compute its path, and then those problems are easy to solve because today there are a lot of efficient shortest path algorithm. Whether or not you need to have some constraints, resource constraints attached to it. So that's the end of my presentation. So to conclude, my goal throughout that presentation was to present one of the highly studied problem in the context of 5G networks, and to give an overview of some of the different techniques that are used to solve it. But just to repeat what I said at the beginning, I limited myself for these presentations to optimization algorithms, but for sure there are a lot of machine learning algorithms as well, which have been proposed in the recent past. So that's all for my presentation.
Thank you very much, Brigitte, for this presentation.